So I was going to talk a bit about the resource management stuff, and we can do with systemd now, and the basis of this technology as what we can do with this. So in general, the problem that we have is that we have limited resources on the CPU laptop. So we have limited CPU time, we have limited memory, which needs to be distributed across caches, data. We need to also do I/O scheduling and ensure that everything receives its fair share of resources. And historically, what we have been doing is that we have distributed those between processes. So if you run a lot of processes, then they can kill the system. And if you fork, like if you run a make J or something like that, and you have some possibilities like setting a nice value or setting U limits, but it's generally relatively restricted to always managing a single process. So we end up treating most processes as equals. However, that means that like a compile job which launches, I don't know, 8 jobs, 16 jobs, how many ever cores you have, might drown out other processes, or a browser uses separate processes, but then renders one page in one of these processes, and then you have a make running, taking up all the rest of the system, and your browser doesn't get all the resources it's requesting, even though your make job, your compile job, is already taking more resources than the browser itself, but one is running on one core only, and the other one is running on multiple cores. And then we end up with an unfair distribution of resources between these kind of applications, which is obviously not something that is desirable to us. So in general, what would we like to have here? We would like to treat users equally. So if I have multiple users logged in, it would make sense to allocate the same amount of resources to each user. So if one user runs a compile job with a lot of jobs and the other one is just doing a single process task, that single process task should run at full speed, while the compile job is throttled down as it's running on multiple cores and actually gets a higher share of resources overall. Similar between applications, the example from before. And in general, we also want to keep the desktop responsive. So if GNOME shell needs resources, I/O access, or memory, or CPU time, it's probably a good idea to give it a higher share of the overall resources than the applications are getting. Which then also, once we do that, and once we actually are able to treat them equally, we can also go one step further and discriminate them. So we'll pick out, and GNOME shell should be more responsive, right? So we'll give it an advantage overall. We could give the active user a better, higher share, or we could also make a difference whether an application is focused or not. So David Atkinson actually created a demo for that I just wanted to quickly share a video. Wait a minute, entire screen. Share. So what you can see here is that 2 processes are going to be started, and each one is running a spinner. And the speed at which the spinner is updated depends on how much CPU resources that program gets. And you'll notice that the currently focused application is running very nicely and smoothly, while the other application is running really laggy and lagging behind. So the one with the dark bar at the top is basically smooth, and the one with the white bar at the top is running slowly. And this is basically a demonstration of what you could do if you discriminate based on whether an application is focused or not. Right, so how can we do this? And the solution for this is on a low level in Linux. are cgroups. So what cgroups basically, with cgroups, what you do is you order the whole system and the processes running in it in a hierarchical structure. And systemd will hide all this away, and systemd does a few things special in the sense that processes are only going to be running in all the leaf nodes, and the in between nodes are not going to run any processes, but that's not a kernel limitation. And then, based on top of this hierarchy that we have, we can then schedule on, then there are controllers available, so we can enable the CPU, I/O, or memory controllers. And there are a number of other controllers that I'm not going to go into because they're not as relevant for us. So one interesting command for you guys might be systemd cgls, so it's cgroup ls, and it'll show you the overall hierarchy of the system. So this would be like my system running a few days ago. So I have dash.slice, which is the root. Then you have the users, all the user processes are in there. Then user 1000, all of my processes are in there. Then this one is the systemd user instance, which runs my session, because my session is launched using systemd. And then I have reordered my session so that all the really important processes are in session.slice. And then you see that GSD is here and GNOME shell is here. And GNOME shell, you can also see that it launches IBUS, for example, right? And XWayland. So it's actually because GNOME shell launches these, they are grouped together as one, and you can consider them as one entity. So then we have the CPU controller, and what we get there is that we can read out certain information from sysfs, from the cgroup file system in sysfs cgroup. So we can look at the CPU statistics per slice per cgroup. We can look at the pressure information, so how often the processes are waiting on actually receiving CPU time and are unable to run because of that. We can change the CPU weight, so we can change the relevance, how relevant one cgroup is compared to another sibling of it. So this is the example from before, where one of the spinners was running faster than the other. What we did there was change the CPU weight to be really high for one of them and very low for the other, meaning that all of the CPU time was going to one of those processes. And then you can configure a few other things like maximum CPU time usages and stuff like that, which is not that interesting for us, I think, but it might still be interesting eventually. Then we have the I/O controller. So this is, again, statistics and pressure information if we are waiting on I/O. We have I/O wait, again, the same thing for CPU, just for I/O. And then there's latency, I/O latency, which allows you to configure latency guarantees. And then if these latency guarantees are not met, basically the I/O wait, the cgroup is going to get a higher priority automatically by the kernel. But the problem there with this is that you must know the disk speed. So it's not very useful for us. And it's not really that relevant, because just setting I/O wait and saying GNOME shell has the same right to the, so the important session processes have the same right to receive I/O as all the applications have. That would mean if the share is 50-50, and GNOME shell doesn't need much I/O, so it'll probably be fine, and it won't be drowned out. So it's already enough to just enable the controller for us. And the other problem with I/O controller is that it requires more configuration work that systemd doesn't do yet. So you actually need to poke files in sys to enable it properly. And the further limitation right now is that it apparently only works really well on Btrfs on a plain partition. So unfortunately, it doesn't allow us it doesn't help us right now, but once it does, it will allow us for proper separation, because then even if one application is thrashing and waiting on I/O and stuff like that, and the disk, then the other application will still receive resources and can keep running, even though the system is overloaded in theory. So we can actually properly separate everything. And finally, we have the memory controller. which again, same thing. We can get the statistic, we can get the pressure information. So how often are we waiting for memory to be loaded? This is either swapped back in or page faults. It might also be page faults, I believe, for file caches. So executables, for example, if they have been evicted from the cache. And then we have other controls like memory low and memory high, which allow us to protect this part of the system from memory reclaim, so it's not going to be swapped out, or the other way around, to basically say this is not shouldn't grow larger, and it will be very slowed down if it tries to. The most useful one here is memory low for us, because then we can say, basically it means this part of the system, treat it as if it's using less memory by this amount. So if you say, I don't know, memory low is 200 megabytes, and I have a 200 megabytes, and I have a 400 megabyte process, it'll compete as if it only has 200 megabytes in memory. And lastly, we also have the ORM group, which basically means kill all of these group together rather than killing a single process, which may make sense in some situations, but it probably wouldn't make sense to kill all of your entire browser just because one of the processes needs too much memory and you need to make room. So killing one of the rendering tab renderers is probably sufficient. You wouldn't want to kill the whole browser in that case. But in other workloads, it could make sense to kill the whole workload at one go. So let's just do a very quick demonstration of this so that you can see what's going on. Share my screen again. Share. So I'm just going to use two GNOME terminal tabs because it's very simple, and GNOME terminal already puts each of these into separate C groups. So I'm going to start one stress ng in one terminal tab, and I'm going to pin it to CPU 0 just to make sure that they are actually competing on the same CPU. And I'm going to start two in another tab. So what we're seeing now is that these three processes are all getting about 1/3 of the CPU time. This is exactly what we would expect from a system not running C groups. All of these processes are treated as equals, and they receive 1/3 of CPU 0. So now what I can do is that added 4. So I added the unit. Let me first show that. So I can now read in proc, I can now read out the C group information, which is all this long path. And this is the, let me choose this C group. I am in the C group where the one of the processes is running. And if I now go in the top one C group up and look at the controllers, you can see that here it's only memory and PIDs listed. What's not listed is CPU. So CPU is currently disabled. So if I now set a CPU wait on both of these tabs basically in systemd, and I just store that, what will happen is that it enables the CPU controller, so it's now listed here. And if I now look at top, what you will see is that test 1, so the first tab, is getting about 50% of the CPU. And test 2, the two together, are also receiving together half of the CPU. So now we are scheduling both applications, both tabs, fairly against each other, rather advantaging the one which is running two tasks. Let's kill all this again and go back. Right. So this is cool, and we can already use this. I mean, we just need to set it up correctly in systemd. It does everything for us. It will group everything nicely in a hierarchy for us. We can control the relevant knobs, which is mostly these three: memory low, CPU wait, and I/O wait. However, it would make sense to be able to tell which application is running, for example. So we want to encode some more information into, structure it in a way that is more useful to us. So this is why we developed it. This was with David Edmondson also worked with this, and the systemd people. We discussed this last FOSDEM. And the draft is actually committed into the systemd repository, so you can look it up there. But basically, the idea is that we'll split the user into 3 parts. So we have a session slice, which is the important stuff that you really want to protect and you want to keep running. Then you have app slice, which is the normal applications, and then background slice in case you have some background tasks like, I don't know, running a backup or something, which really shouldn't compete with slow down your applications if it's running. Another thing that we want to do is encode the application ID in the systemd unit name so that we can figure out which application the process belongs to. So this allows us to do everything. And we can also, for example, create the task manager, improve the task manager that way, and manage per application resources if we actually containerize the applications in that way. This is an example of the KDE one, where you can see that Spotify here is grouped together, and you can see the different processes belonging to it. This is something that I think David Edmondson did this demo. Might be committed even, I'm not sure about that one. Correct me. And then the other day, I tried this out in GNOME usage. So what you'll notice here is that this is the before. So the web, I was using Epiphany at the time. It's clocking it at 567 megabytes. But it's also funny that the system is using 3.4 gigabytes. But then if you actually start fishing the application ID from the cgroup information that is already there and present, the picture changes quite a lot. The system only uses 1.8 gigabytes, so that's all of the stuff that can't be grouped. And web is using 2.1 gigabyte. So you can really see that the heuristic that we used there was not able to pick up the fact that web was actually spawning separate processes for the rendering tasks that used up most of the memory. Right. So next thing was, the idea was to separate everything out and create this session slice and stuff like that. And we also had discussions in Fedora about early ORM and protecting all the system against thrashing situations. And what came up there was that with all this infrastructure and being able to set memory low, we can actually be smarter about this, because we could give an allocation of memory to the session, to the core processes, to the important ones, and then try to ensure that if something starts thrashing, it's going to mostly hit the processes that are not as relevant. And everything is there. We have all the low-level tasks done, basically. We basically just need to drop in a lot of configuration files and enable it. So for GNOME, this means making it more conformant to the systemd through the conventions that we have defined, as GNOME upstream is not yet as conformant. But this is very simple to do with a few drop-in configurations. And then the uResource daemon that I quickly hacked up, it basically tracks which session is active on each seed. And based on that, it will delegate 250 megabytes. That's the default configuration to the active user. And this is then also further delegated to session.slice. So basically, all the important session processes like GNOME shell, GNOME settings daemon, they do get a memory guarantee of 250 megabytes this way, and are treated as if they use 250 megs less on overall. And it also means that they should get better behavior in low-level memory situations. They will not lose their file caches if someone else needs that memory. So they should be a lot smoother if it comes into weird situations where there's not enough resources available. It also, because it's easy to do, it'll just give a higher priority to the active user. So right now on my system, if I logged in through SSH as a root and ran the same stress-ng test, it would get 20% of the CPU time or something, and my stress-ng test running at the same time would get the rest. Yeah, so the effect is that by enabling the CPU cgroup controller, our applications are going to compete equally. The active user is going to receive a greater share of the CPU, and the session is effectively protected from thrashing, because thrashing situations is usually memory waiting for memory, and because it has memory of its own, it's not going to be as affected as the applications. In the extreme case, it might be that all of your applications are completely frozen, but GNOME Shell is still responsive. It's probably not going to be that good in reality, but that's it. So yeah, this is pretty neat overall. What's a bit of a shame is it's hard to test this. I would have loved to actually demonstrate this working very well, but creating artificial situations that thrash doesn't seem to be that easy. I'm not sure. I don't have a very good test to try this out, to be honest. Yeah. So yeah, and you can't fork bump. Like if I ran a fork bump in one of my terminals, it just wouldn't do anything really. It would just hang GNOME terminal. So if you want to use this, if you want to try this on Fedora 32, just install it. It's really that simple. It'll drop in a few configurations. You need to enable the service, and then you reboot. I've actually proposed this as a change request for Fedora 33. Maybe we'll do this by default. Otherwise, just grab the sources and try it out. It's really safe. Like there's just a few drop-in configurations, and there's not much that can go wrong there. So it's probably could be fun trying it out. In the future, I would like all of this to die, to be honest. Like the daemon is, most of the stuff that's in there should be upstreamed elsewhere. So the systemd units in GNOME need to be updated, obviously. Some configurations will need to be changed on the systemd level so that the whole delegation process works. And the policy itself to give resources to the active user, we will probably need to find a new place for that, because it doesn't really make sense to just have a daemon running just for that purpose. It might be systemd login as a pretty obvious choice, but it doesn't feel quite like the right place. So I'm not quite sure yet. Open to suggestions, obviously. And yeah, so just as a quick overview of what there is to do on the GNOME site and systemd related. So we should become more compliant with the systemd conventions that we discussed. So we should add the task manager, so that's also clear. One of the biggest issues at this point, other than finally merging some of the systemd cleanups that's going on, is that we need some new APIs. So if I have a chat program, start launching my browser, and the browser wasn't running, it shouldn't end up in the same C group as the chat application. It should get its own C group. And it's not quite clear. The glib APIs basically just launch the process, and then you either need to move it into a new scope, or the alternative is probably to just go through the next DG portal or something like that and delegate the launching to someone else, to another service, which then can ensure that the systemd hierarchy is correct. And then there are some other things going on also. So systemd OMD is just going to be merged very soon, and we should probably look into using that. So this is systemd OMD as a information. Basically, the approach is there. What you do is you measure whether the system is thrashing, and if you detected thrashing, then you'll start killing processes. So you don't wait until you're out of memory, but you wait until the point where you notice everything is actually slowing down. The bit of a problem with that is that it's always slower, because you need to measure for a while. So it'll measure for like 60 seconds. And if in those 60 seconds, more than a certain amount of time was spent waiting on the disk, at that point you go, well, this is probably bad. I'm just going to kill some process. That's the general idea here. And then we also need to figure system need to become a bit smarter about cost models. There are some rough edges still. And for like people using Lux, you probably want device mapper support for the IO scheduler. All right, that's it from me for now. I'm going to, as I understand it, the questions are in the other pad, right? Where's the other pad
there? The other pad with the questions is in the shared notes on the left.
Yeah, I'm just, oh, sure, yeah. I don't think I had it open yet. Questions. If a full screen game is running, could this have extra weight given to it? Yes. So that was basically the
Excuse me, please read out the questions aloud for everybody.
So the first
Before
question was, if a full screen game or unredirected window is running, could this have extra weight given to it? This is actually the exact example, basically, that of the demonstration from David Edmondson. So that what was going on there was that the window manager or something detected which window was active, and then it gave a higher CPU share, CPU weight to that application. And obviously, as long as you are able to detect which application is actually focused at the time, you can do that. It's not a problem at all. You could also do other things like freeze the application completely or something like that. All right, second question. Once apps and services are in a systemd tree, what work would need to be done to the systemd part of the stack to allow for restarting of the session without losing running apps and services? Interesting. So right now what we do is actually ensure that everything shuts down, mostly. So what would happen currently is that we have a virtual target called graphical session.target. And when we log out, we ensure that this target is stopped. So anything that binds to or is part of this target will be stopped automatically. And in GNOME, what we actually also do is that we restart the debus daemon when you log out. So just to make sure that evolution is dead, which is really a workaround for evolution not having the graphical session.target or something like that in its systemd unit. You could already do that if the application is smart enough, but the problem is that you won't be able to connect to Wayland and stuff like that. The environment variables that you're getting at the start to connect to Wayland will be wrong. For a debus service, it would work, except that we restart the debus daemon right now as a workaround. Yeah, so not great, the situation. Also remember that 10 seconds after you log out, the last session is closed. Systemd will generally stop your user instance. So at that point, all your user processes will be gone anyway. When a laptop is on battery mode, can we be more aggressive to non-focused apps and give them less CPU time to save power? This is interesting. I think from a kernel perspective, we can, because we have the, let me go back to the slide. We have the CPU.max and stuff like that, and there you could say something like, in a 100 millisecond slice, it's only allowed to get 10 milliseconds of CPU time, or something like that, I think. So CPU.max, and there are some other controls you would need to check. It could be that systemd doesn't allow you to set these yet, so you might need to look this up either in systemd to do it properly, or you may need to write to the cgroup hierarchy directly, which wouldn't be as nice. So it would be probably be a lot better to, yeah, not do that. To first integrate into systemd and then implement something on top of that. But I'm not sure what is actually sensible there. You probably want something else, like monitoring how much CPU it's using, and then telling the user that this application is doing something bad. How does unmerged systemd OMD fit into the picture? All right, this is a bit more complicated. So as I see it, the problem that we have is, in general, this is about the situation where the system might be starting to thrash, and you run into low memory situations where you need to kill a process to get the system back to working. And in general, as I see it, there are two ways of handling it. One is being proactive about it, like we protect the sessions, we give it memory. The other way of being proactive about it would be a system like early OOM, which simply, well, basically, in my view, it effectively ensures that you have enough memory for file caches. which are essential because your applications are nothing else but binaries on disk when they are running. And then you have systemd OMD, which is like more of a reactive approach where you actually are able to measure that the system is thrashing, and now you only start to kill if things are going bad. And the thing here is that you need something proactive. You don't want the session to be like completely locked for 1 minute because you're measuring over a minute here. So you need to protect the session, and so you need some proactive measure. And right now, this is for in Fedora, at least this is early OM. But if we start to protect the session by allocating memory to it and allocating guaranteed resources to it, then we might be able to, instead of running early OM, switch to systemd OMD. And then we are going to be a lot smarter about which applications we are killing and when are we killing than early OM is with its heuristics. So basically, doing all of this should allow us to move to systemd OMD and be smarter about how and when we are going to kill applications to keep the system running smoothly. Right, next question. Is there something background daemons can do now to opt into improved resource management? Can they already specify background slice somehow? Yes. So all you need to do is wait, I can write here, right? So all you need to do is just do slice equals background.slice in your systemd unit, and that's it. And if you look at what your resourced does, wait, let me share your screen again. So if you look at your resourced, all it's doing is it's dropping in a lot of configuration. So here, GNOME shell service is going to get service, and here it's moved into session slice. So really, that is all there is to it. So if you want to, we moved into background.slice. Background.slice currently doesn't have any configuration yet, but we can add that. All you need to do is, so this was wrong actually, is to write the slice unit there. Whatever. Okay, next question. Can we have something kind of this? Can we have this enabled in GNOME OS? Well, sure. I mean, the easiest thing is to just install your resourced because it does the configurations and does the. And it's important because it needs to assign the memory limits to on the system level. So you need a small system daemon doing it. But yeah, you just installing your resourced should do it. Why is GNOME calendar daemon 2.2 gigabytes? Let me check my slide. Where was this? No, this is evolution. I'm just using evolution. So that's actually not evolution calendar, it's evolution as a whole, which probably explains why it's 2.2 gigabytes, because it just has a shit ton of email in there. Okay, next question. Could you expand on what needs to be done if someone creates their own application launcher so new applications are grouped correctly? Basically, I think the best thing is if we provide a low-level API that everyone should use. Because otherwise well, there are two ways. Either you go to the systemd page and you basically do exactly what it says there, which shouldn't be very hard. It's not that hard. It's just a way of encoding the application ID into the systemd unit name. But you'll need to either launch the application using systemd, or launch the application normally and then move it into a systemd scope. Those two options you have. And it would be a lot easier for everyone if there's a good API and everything will be done correctly. And the same thing is true for Flatpak in my view, because Flatpak is basically needs the same, has the same issues, right? Because you might need to launch an external link or something like that outside of a Flatpak. Okay, next question is Flatpak start unit scopes for each app in the user session. Can these be auto-moved to background if it matches some setting or such? This is interesting. So what you can do is you could, there are different ways of doing this. One thing is that Flatpak already needs to generate a unit configuration. So if Flatpak knows this should be running in the background, then it could just explicitly move it into the background right away. The other thing is if you as a user want to do it around Flatpak, you could configure it through systemd directly. So you could create a file that basically says, okay, this Flatpak with this application ID should be moved into background.slice. And you could then also like set your own limits and tell it that it can only use 1 GB of memory or something like that. I actually did that for fun for my evolution, so it could not eat more than 1.5 GB or something like that. And it worked. Like at some point, the kernel would just OM kill the process and it would just restart evolution, and I would be happy because it wouldn't eat quite as much RAM, because it was leaking quite a lot at the time. It's actually got a lot better now with the new Fedora version. Okay. I think that's it for now. I'm happy to say more.
You can have 5 more minutes if you want.
Yeah, but so if someone asks a question, I'm happy I'm going to answer it, but I'm not sure what I should talk about. We have people typing. The whole system deboot. Of course, we want to do everything with systemd, obviously. G-memory monitor, what is that? Oh, G-memory monitor looks at pressure information, right? All right, so the question was, how does this interact with G-memory monitor? And so the G-memory monitor looks at, let me just share my screen. It will look at proc pressure memory, I believe. What you can see here is how often some applications and this whole system is waiting on memory. So these statistics will still be correct. However, if we are protecting the slice now, then some parts of the system will still be running smoothly and other parts might not be running smoothly. So I do expect that it might skew these statistics slightly, so the full statistics, because if GNOME Shell is actually doing, like the session is actually doing work and it has a protection, so it's actually getting work done and some other parts are not getting any work done, then the sum line will say, ooh, everything is out of whack, we're not getting anything done, because there's some process that really doesn't get anything done. But the full system overall is still maxing out the CPU. It's not waiting on the disk because there are some processes that are getting their work done and they are getting enough I/O resources. So I imagine that in some situations it could skew these statistics a bit more. It probably shouldn't be that bad. Like you could already get into the same situation today if there's a small process just crunching away on the CPU, and then yeah, it's not going to run into memory pressure. So the full system is always doing something useful. So the full line will not show anything, but the sum line will show something. That could also happen now. Okay, what else? are those changes for resource management also compatible with older systemd version systems without systemd? Systems without systemd, absolutely not. Like there's just no way of doing this without cgroups and something that manages the cgroups for us. Older systemd versions is already problematic. So like some of this stuff, I just proposed a patch today to improve systemd to make this work better. So yeah, so even systemd versions, we might need to create new versions for all this to work quite well. Yeah. So okay, I think that's it then. What will be in GNOME? Okay, like just quickly, what will be in GNOME 3.38? I'm planning to get the restructuring of the session into GNOME 3.38, a few cleanups maybe, but you'll need stuff from out externally, like your resource-d or something like that, to actually get any benefits. I don't think it makes sense to enable the cgroup controller yet from GNOME side. All right, I'm done then. Sorry for not answering the last question.
Thank you very much. You can still try to answer the question over the chat. There is a link in the shared notes. We can continue the discussion over there.
All right.
Thank you very much.